Um, all right, maybe we should get started now. So welcome everyone to lecture 2 of CS 545. So today will be about linear algebra review. So today and the next class next week will be on the math review that hopefully mostly familiar to you. So, if you find that a lot of the material that we're covering is new to you, then you might want to talk to me and see if your background is suitable for the class. And just a couple of logistical things. So if you do want to ask questions, I'm using the same Google Doc as I did last time. So it's the same Google Doc link that if you go on Piazza, you can type in your question there if you prefer that, or you can just raise your hand and ask normally. We updated the website with the office hours for both TAs. So the TA will have office hours on Thursdays and Fridays. So the first one should be tomorrow. So look at the course website for all that information. Right. Any logistical questions before we move on to the details? Yeah, and especially for today's lecture and for some of the ones going forward, it might help if you have like an iPad and iPad pen or just normal pen and paper. If you remember how to use those, then you can go through some of the math that we're using that we're going to go through here. So sometimes I'll try to pause and then say, can you solve it? And then I'll wait a few minutes and then see if you got it. Yeah. But nothing here is going to be graded. It's just for your own exercise and benefit. All right, so let's get started then. So linear algebra. So linear algebra is an incredibly important branch of mathematics. And if I had to summarize it, it would be that it gives us a way of being able to compactly represent and operate on sets of linear equations. So if you look at the two equations that we have, maybe we have those equations and the objective here is to solve for x. So what is x1 and x2? Now, if you just had those, just two lines, then you can solve the first equation for x1. You find that value, then you plug it in for x2, and then you determine, what the values are from that. But what if you have maybe 100 of these equations? And more generally, linear algebra gives a nice way to describe this system of equations very compactly. And I'm hoping many of you have seen the AX equals B convention, which describes this linear equation where the matrix A gives us the coefficient for the x's, and then the B represents, what the equality. But of course, there's also more to linear algebra than just the notational saving. There's also a lot of powerful analysis and tools that it gives us when we're trying to analyze, linear equation or many things that appear in robotics, especially when we deal with higher dimension, when we have vectors that have a lot of elements in them. So linear algebra is a very incredibly important tool. So vectors. So a vector of this dimension n is basically an array of n elements. So here we're going to consider all real numbers. So I don't think we have to deal with complex numbers for now. Just assume that they're all real numbers. And pretty important point is that when we write a vector like x, we're going to assume that it's a column vector. And that way, when we write it out, it's going to be like x equals, and then you write the individual item, x1, x2, all the way down to xn. They're going to be in a column like that. And now this is standard notation, not only for this class, but also for most other classes. And so, sometimes you'll have to deal with notation that's a little bit different. So sometimes people bold X, sometimes it's not in italics like that. So hopefully the meaning of what it is should be clear from context. And this is also partially what we call like mathematical maturity. Like there might be different, notations that people use, but if you're familiar with vectors, usually the meaning will be clear from context. And yeah, and then we use the transpose operation. So if we want to express something, like that looks like a row, then just put x to the t over there. That's a transpose. Yeah, so hopefully everyone has seen that. All right, vector norm. So we have vectors, and norms are functions that basically tell us, what is the length of a vector? That's the informal way to think of a norm. So formally, a norm is really any function that satisfies these four properties. Well, the first, it's got to be non-negative. So if the length is negative, it gets a little bit confusing. So the length here is just going to be positive. And it's only going to be zero if x is a zero vector. That's the second condition. And then the third and fourth conditions are like homogeneity and the triangle inequality. You can kind of see what they mean. If you have a scalar t, then you can pull out the scalar, but you have to take an absolute value on it to make it positive. And then there's the triangle inequality, which hopefully you've seen before. It basically says that f of x plus y is less than or equal to f of x plus f of y. And some of the common norms that you have probably seen are the Euclidean norms. So that's what this means. Usually when we put functions that are norm, we put in the two vertical bars to the left and the right, and then the two indicate that it's the Euclidean norm. But it's also so common that when people talk about norm and they don't put the two there or any number, we just assume it's Euclidean. So what are some of the other norms that you've seen? Yeah.
L1 to the L2.
Yeah, well, I think by L2 you mean the Euclidean. Yeah. So more generally, there's the LP norm family where you can have x of p, where this is some integer, and then you have this term, and then you raise it to the 1 over p power. So if you have the 2 norm, the exponent is 1/2, that's the square root. If you have the L1 norm, you just don't, you have the absolute value of everything, basically. All right, inner product. So if you have two vectors and their dimensions are the same, which is pretty important here, then the inner product, before we move on, question? All right, so why would you use one norm over the other? So there's different reasons that people use different norms. So like if you're trying to do something like, say, train a machine learning model to minimize some errors, you might want to penalize errors that are further away, like more, and you could do that. Like with the L2 norm, it penalizes errors more so relative to it penalizes outliers more than the L1 norm does. Like that's one way to think about it. Like different norms like penalize different parts of your errors differently. So I think for this class we're mostly focusing on the Euclidean norm. So but people use different norms for different reasons. So yeah. All right. So inner products and dot products and scalar products. So those are three terms that, for our purposes, they're going to be equivalent. So if you're dealing with the more advanced mathematics, then technically the terms have some different meaning, but here they're going to be the same thing. So it basically means that if you write it out like this, x times y, although you need the transpose there, that's important. You can express it out symbolically as, like a row vector of x and a column vector of y. And then the result is just the sum of, xi and yi for all I. And because we're dealing with just a sum over a bunch of scalar terms, then you can always like flip the order. So it's like if you have two scalars, a times b, you can flip it as b times a. And the same thing applies here for the inner product. And hopefully everyone sees like why this is true. So if you have the Euclidean norm and you square it, it's the same thing as this thing. Because like in the previous slide, we had the square root here. And so now we're just squaring that. Yeah. All right. So two vectors are orthogonal when their inner product is 0. So x times y is 0, and a unit vector has a norm of 1 if its inner product with itself is 1. And we can always normalize the vector to make it a unit vector just by taking the vector and dividing everything by its norm. So everyone sees why this is true. So like if you take the norm of this, then you have the norm of this whole thing, and then the bottom part will move out. In fact, I could just quickly do some stuff here if you want me to look at it. Yeah. So for the bottom part, if you have this, then like basically what happens is this part goes out. Yeah. All right. So to get a little more intuition and some examples, then you can also think of the inner product as this formula, where you have the product of the norms of x and y, the Euclidean norm, multiplied by the cosine of theta, where theta is the angle between the two vectors. So if the angle is 90 degrees, then the cosine of 90 is 0, sorry, then the inner product is 0. And so you get vectors that are perpendicular to each other. And on the other end of the spectrum, then if you have the cosine of 0, which is 1, then the inner product of x and y is in some sense maximized, like they're pointing in the same general direction. So the norm is just the inner product is just the product of the two norms. So. All right, so we have the inner product. So we should now discuss the cross product. So the cross product is defined over two vectors in 3D space, and the formula there is written over there, but it also doesn't give too much intuition, so we'll cover that in the next slide. Although before we move on, I do want to mention that you can also define a matrix operator, and then if you define this matrix and you do like a left multiplication on a vector, then that's like taking the cross product between two vectors. And you can verify this algebraically just by going through and doing the standard matrix vector product computation. So the cross product of x and y is the same as this S of x matrix multiplied by y. So the intuition here is if you have two vectors, A and B, then the cross product is the one that is perpendicular to both. But if you notice that there's actually, it's somewhat ambiguous. There's like, you can be perpendicular in either direction in that case. So that's why people usually deal with the right-hand rule. I assume because most people are right-handed like me. So the index finger is A, the middle finger is B, and then A cross B is the direction of the thumb. So, and you can, if you orient your hand so that it matches that, you should be able to get the same thing. Although so sometimes just a caveat, like if you're working with some code bases, I worked with some code where for some reason they actually didn't seem to follow the right-hand rules. So if you are working with code that deal with like rotation and stuff, just double check that it's following the right-hand rule. It really should, but I had to complain to some people. All right, so those were some vectors, and you also did see an example of a matrix, but let's cover this a little more formally. So this is how you might write out a matrix. So one of the references that I linked to for today's reading, they use this notation where like a bracket for Aij. I personally don't use it that much. I usually just use the letter or just write it out, kind of like how they did it over there. So this is an example of a matrix with dimension m by n. So those are the number of rows and the number of columns. So whenever you think of matrices, always think of it as row by column, never column by row. But yeah, and sometimes people will use boldface capital letter, and other times people just use the capital letter. But I guess the point is the consistent thing that people do use for matrices are capital letters, and usually people just use A, B, C, and then maybe sometimes D. Very rarely E and other and going on after that. With some exception, which we'll cover later too. Oh yeah, this is a matrix. It describes all the numbers together. So if m is the same as n, then the number of rows is the same as the number of columns. So we call that a square matrix. So if m is less than n, then there is more columns than rows. So think of the number of columns, but having many more, so it stretches out horizontally. So that's why we sometimes call it a wide or fat matrix. And if the other case holds, then there's more rows than columns, so the number of rows keeps increasing until you get a very tall matrix or skinny matrix. And a special case of what we've seen earlier is when n is 1, then it's reduced to just a column vector. Yeah. All right, so upper triangular matrices. So, and these are only for, well, we're only going to consider square matrices here. So for a square matrix, it's said to be upper triangular if it looks like this. So there's a formula here, but I find it easier to visualize just by writing out some of the numbers. So it's upper triangular if you see the diagonal of the matrix, everything intuitively below it should be 0. And that's this region here. I mean, the actual diagonal stuff, it can have whatever. It just needs to be off diagonal and below it. So if it's 0, it's upper triangular. What about lower triangular? Yeah, it's basically it's the same thing, except the zeros go in the direction in the opposite side of the matrix. Yep. And another special case of a matrix is one when we have a diagonal matrix. So that means that all the off diagonals are 0. And that way we can more compactly, well, maybe more compactly write the matrix like that. It's like diag with all the stuff that all the diagonals there. What if it's all one to the diagonal? What's it called? Yeah, identity matrix. Yeah. All right, the transpose of matrix that is of dimension m by n is the n by m matrix, which is obtained by flipping the rows and columns. So if we have A here, then the transpose is AT, and basically just means if whatever is here, A21, it needs to go to where A12 is, and vice versa. And so that's why you see here A12 and A21 have flipped. Yeah. And if you look at other fields, like sometimes I've seen people write A prime to indicate the transpose. I really don't like that notation. So here we're just gonna stick with the T here. Or if you're using LaTeX, you can sometimes use, the top command, like something like that. And you might be able to get the transpose as well. But you can just use the T, it's fine. All right, so what's the transpose of the following matrix? You should be able to do it in 2 seconds. All right. Everyone got it? Okay. All right, so what about symmetric matrices? So a symmetric matrix, which we're only going to consider square matrices here. So symmetric means A transpose is equal to A. Well, that means if you write it out symbolically, then whatever is in A12 must equal whatever is here. That's why we just duplicate these numbers. Yeah. All right, so some examples of symmetric matrices are, this matrix and this matrix for n greater than or equal to 1. So that's the identity matrix. That's another shorthand for how we write it. Sometimes we just don't write the n if it's just implied. All right, so skew symmetric matrices. So a skew symmetric matrix is one where A transpose is equal to negative A. Visually, it looks like this. Because the transpose operator doesn't change the diagonal, and because we're negating matrix A, then we need the diagonal to be 0. And for the off diagonal, we just have to make sure that, whatever is here at the position of row 1, column 2 must be the same as column 2, row 1, but negated. And so that's the pattern that we need to see for a skew symmetric matrix. All right, so let's discuss some basic matrix algebra. So if the matrices have the same shape or the same dimension, like the number of rows and the number of columns, then if we have, A plus B, then it's the same as B plus A. You can also I will C equals A plus B, but basically the intention is that if they're the same shape, you can do matrix addition. Like if you're adding 2 matrices, they need to be the same shape. And you can also have a similar grouping property where you can add A and B first and then C, or just add B and C first and then add in A. And so if we have a scalar like alpha, then the matrix, alpha times A is the same as the matrix A, but every single item in it is multiplied by that same scalar. All right, so for any square matrix, if we have AS and AA, which sometimes we call that the symmetric part and the skew symmetric part, then you can express it for any square matrix, A equals AS plus AA. So that's just a way that we can universally split up, in some sense, split up a matrix into 2 different parts. And sometimes this becomes a useful algebraic tool that you might use for some calculation. So here's an example. Suppose we have A and A transpose here. Then what would the expression be like if we had A equals AS plus AA. And I'll give you a couple of seconds to work it out. You might be able to do it in your head if you can. Yeah. So the symmetric part looks like that. So if you take A and A transpose, and then you add them up, and then you divide it by 2, you get this thing. So the 1 and the 4 are basically the same. The 2 and the 3, you have to flip. You flip the 2. You just add in 2 and 3 and 3 and 2, and then you get the same thing. It's a symmetric part. The skew symmetric part would be A of lowercase a there, and then we just add them up. You should get the original matrix A. All right, matrix multiplication. So when we're given matrices of appropriate shape, and the shaping is very important, we'll talk about that soon, then these following properties will hold. So for example, you can do something like you can add in B plus C in parentheses first, and you can distribute the matrix A just like if they were scalars to get AB plus AC. For the transpose operator that we talked about earlier, whenever you're transposing something that has 2 matrices inside, you have to flip the ordering and then you transpose both of them. If you have 3 things like A, B, C transpose, then just treat A, B as one matrix and C as the second matrix. And then you do the transpose and reordering on both, and then you repeat the process for A, B. So. Now the dimension check, so every time, especially when you're dealing with software that does matrix multiplication, I highly recommend printing the shapes of the matrices. So for this to work, for matrices m by n and n by p, like we need this number and this number to be the same. So the second number of the first, the number of columns of the first must equal the number of rows of the second. And when we do this, we result in an m by p matrix. Right. So personally, I find this most useful when I'm debugging like PyTorch code and I have to print out the shape of something, and then I've caught a lot of errors that way. So just always double check the shaping. Yeah. So is this true? Yeah. I mean, I guess if it was true, then I probably would just put it in the original list, right? But let's just go through an example. So maybe you can just quickly do the matrix algebra in your head. I mean, if you're not familiar, the way to just do matrix multiplication, like if you have A times B, you go through the first row and then the first column. You do a dot product there, then that becomes the upper left item in the product, and then you just repeat for all the rows and the column combination. So hopefully everyone has gone through the computation, but I mean, I'll put it out here for you anyway. So in these cases, they're not equal. So hopefully you're able to get the A, B, and BA matrix value. Yeah. All right, so going back to when we talked about the inner product, so the inner product is basically a special case of matrix multiplication. It's just that you have 2 vectors instead of 2 matrices, although a vector is a special case of a matrix, but I usually think of a matrix that like having more rows and columns than just one. Yeah, so if you have X times Y, then you go through and sum up the product of all the matching X and Y components. And from a dimension perspective, remember that it's 1 by n multiplied by an n by 1 matrix. And then you get a 1 by 1, which is the same thing as a scalar. So no, that was the inner product. So the outer product is something different, and it's a little bit more to think about, but it's kind of like it's like the inverse to some extent. But if you just think of two vectors x and y, then this is what the outer product looks like. Because we deal with column vectors by default, the x here is just this column vector, and then y transpose is the row. And so we have an m by 1 matrix multiplied by a 1 by n matrix. And then you get an m by n matrix. It's just that when you're doing this, each component is just like the product of two scalars. So it's like you start with the first row of x and the first column of y. Then x1 times y1, that's your upper left item. And then you just continue for all the possible row and column combinations. So, yeah, so hopefully the idea of an outer product is very intuitive. So any question about all the stuff that we've covered? It should be mostly review, but I just want to answer any questions if I can. All right, inverse matrices. So if we have a square matrix A, then it's invertible or non-singular if an inverse matrix exists. So we write that out as A to the power of -1. So if the inverse doesn't exist, then it's non-invertible or singular. And you can write it out like A inverse multiplied by A is the same as the identity, which is the same as A times A inverse. And yeah, just watch out for some of the potentially confusing wording. So you might think non-singular and non-invertible. They both use non at the start. So they must mean the same thing? Well, no, they actually mean the opposite. So just be aware of the potentially confusing terminology. So I'm not sure who made that decision, but we just have to live with it. Yeah. And yeah, if the matrix is non-square, then there's no inverse. Yeah, so not all, even if you have a square matrix, they might still not have an inverse. So some matrices just don't have inverses. Yeah, so some of the properties that are hopefully familiar are that if you have A and B of appropriate shape, then if you apply an inverse on an existing inverse, then they basically cancel out. And it's kind of the same thing that you had with the transpose. If you have A, B, their product, and then you want the inverse, then you flip the ordering of A and B, and then you apply the inverse on both of them. And if you have inverses and transposes, then you can essentially reorder them. So these are some basic properties. If they're not immediately apparent, then just do some simple 2x2 matrix example, then I think it'll become clear. All right, so orthogonal matrices. So if we have a square matrix and the condition holds that A transpose is the same as A inverse, then the matrix is orthogonal. So remember that by definition of an inverse, if you had A inverse times A, then that would be the identity. But with an orthogonal matrix, you can substitute it with the transpose. And by the way, just as one reason why this is useful to know, like computing the transpose of a matrix is much easier than computing an inverse. So the transpose, you flip things around. With an inverse, you have to get to some sophisticated algorithm to even get close to like something below cubic polynomial cubic time. So yeah, and these are what we call orthogonal matrices. They come up a lot in linear algebra and also machine learning as well and other related fields. All right, linear independence. So if you have n vectors, each of them have m items, then they're linearly independent. If this expression, if it's equal to the zero vector, only when all the constants, k1, k2, and up to kn, they have to be zero. So if there exists some values of these k's where they make the whole sum zero, but the k values are not non-zero, if they're non-zero, then they're linearly dependent. So that means you can just write one vector as the linear combination of all the others. Yeah. And you can, so symbolically, you can visualize like here, the k's are scalars and then the a's are the column vectors. And they form this matrix A where A1, A2, and AN are all the column vectors. And a condition for linear independence is if the matrix A has rank n, and the rank of a matrix is a very important concept. So the rank of a matrix is the maximal number of linearly independent columns of A. So if you have some matrix and the rank of A is equal to the minimum of the number of rows and the number of columns, it's considered a full rank. If it's easier to think about, just think of M as equal to N, and then you get a square matrix. Then if all the columns are linearly independent, then it's full rank. Yeah. And yeah, we already talked about the linear dependence. So yeah, if one of the vectors can be defined as a linear combination of the other, then they're linearly dependent. So the corresponding matrix would not be full rank. All right, so now we'll talk about some systems of equations. So this was actually from one of the first slides that we had, where if you have the matrix A, the vector X, and the vector B of appropriate shapes, then AX equals B is considered the linear transformation where A is like a linear operator on X, but you can also view it as a system of equation too. So if we have A and B, how do we get X? Any ideas? You might have to make some assumption if you're depending on what solution you're proposing. I saw some hands of, yeah.
So A would probably have to be invertible, and we would have to multiply it basically on both ends so as to get X.
All right, so basically that. So how does this work all the time? Yeah. What happens if A is not square? What if the inverse doesn't exist? Yeah, so this works sometimes, but other times you might have to do some other things if you want to get a solution. And also one thing that I find helpful when I think of the AX equals B is I often have a mental model of the columns of A. So whenever we have A of X, then you can think of A as just a bunch of these column vectors. So those are what the terms mean. And And the x here, again, it's just a vector, so it's a column vector with a bunch of scalars inside. So these terms, the x's, they're all scalars, while the brackets indicate column vectors. And hopefully the system of equation, this way of rewriting it is also clear. So AX is equal to the linear combination of the column weighted by the x. Yeah. So take another look at that if it's not immediately clear. All right, so another term to be aware of is the column space. So the column space is basically the set of all linear combinations of the columns of A. So you can pick different values of the x's, and by doing so, you get a different set of resulting vectors. And then if you consider the whole possible set of values of x, then you get your column space. Yeah. So if we're considering a system AX equals B, then it's solvable if and only if B is in the column space of A. So that means basically there must be some solution of all the x's that will give you B. Right. So what if B is the zero vector? Then for the system AX equals 0, if there is a non-trivial solution, then the matrix A must be singular. And we'll also cover what a determinant means, but the determinant is also 0. So yeah, generally when you're thinking about systems of equations, the AX equals 0 case is also a very important special case to keep in mind. All right, so let's talk about the determinant. So the determinant is the number associated with each square matrix. So it's written in different terms. I mean, using different terminologies. Like I prefer determinant parentheses of A, but you should be prepared to see different conventions. So what's the intuition of the determinant? So it's kind of like the measure of the volume that is taken up by the linear combination of the rows of the matrix. So, you can see there's an explicit formula that you can look at for the determinant, but it doesn't give you very much intuition. So that's why if I describe intuition, I try to think of it as the volume. So here's an example. You have the matrix A that is 1, 3, 3, 2. So the first row of A is A1, which is 1 and 3. The second row of A is 3, 2, so that's 3, 2. And if you try to form a parallelogram in 2D, then the area becomes the determinant. I think the determinant is the area of the parallelogram. Yeah. So what about when the determinant is 0? So that would mean the matrix is singular. And let's suppose what would happen if you have 1, 3, and 3, 2. If we change this row to be 1, 3, let's say you had 1, 3, and 1, 3 as the two rows, then you would get two vectors here. They would coincide. And so what's the area of the parallelogram? It becomes 0. I should also say there is a slight typo that I noticed. Like usually you don't write the absolute values. Usually just write determinant of A. So yeah, just be aware of that. Yeah. Any questions on the volume interpretation? Usually, I think I find this to be mainly helpful for 2D and 3D. Like if it's higher dimension, it's kind of hard to interpret it. Yeah, and there are some formulas. You probably have seen some of the formulas of the matrix determinant, but make sure you don't use them if your matrix is 4x4 or larger. So just use it for 3x3 or smaller. In fact, even for 3x3, just be careful that you don't have any like plus or minus signs flipped and stuff like that. Yeah. And like, visually, like the way I sometimes visualize it is whenever I have a 2D thing, it's like you go through the diagonal this way, and then you flip up, and then you go back like that. So it's like, yeah. So sometimes I just have this as my mental model of how to compute the determinant. So, yeah, hopefully that's a little bit helpful. All right, the matrix trace. So hopefully everyone has seen the trace before. So if you have a square matrix, then the trace is the sum of the diagonal elements. Right. And this is a useful property of the trace. So whenever you have A and B such that A times B is square, then you can reorder A and B and you get the same trace. Can you prove why that's true? So this is basically how you would show that it's true. So you start with the trace of A times B. Now, what is this? This is just a definition of what the trace means, right? So you're summing from I equal 1 to M all the diagonal elements of A times B. So just put that in parentheses, then you put the double I, then that's your diagonal. So the next equality here, if you haven't seen matrix, if you haven't seen matrix multiplication, sometimes maybe it might not be immediately clear what that means, but this is basically what matrix multiplication means. It's the definition. So you can rewrite this as this thing. Is that clear how that works? I can do it on the board if you want, but I just assume that if you want to find this equation, you can just write out the definition of A times B and then match the subscript, and then you'll get that. And then what do we do here? Well, here we just get rid of the parentheses because we're dealing with scalar addition. We have a double sum of a bunch of terms, so it doesn't really matter what order we sum up everything. Everything is a scalar. And that's also what happened here. Like we have a sum of I equal 1 to M, and then we can reorder it with the sum of J equal 1 to N. So, and then from here, we just repeat the process from the first line, and then you get the trace of B times A. So the trace has a number of useful properties. So this is one of them. There are a few others. The reading that I link in the reading for today, it covers a lot more of the useful properties as well. All right, eigenvalue, then eigenvector. So U is some vector, A is some square matrix. If this is true, A times U is equal to lambda times U for a scalar lambda, then lambda is an eigenvalue and U is an eigenvector. So what does that mean? Like you take the vector U, you have the matrix A, you multiply it. That's the same thing as taking U and then scaling it. Either you increase it or you decrease it, depending on what lambda is. Yeah. So the vector would point in, if you plot it in 2D, the vector would point in the same direction. And you can rewrite it. So if you want to be able to solve for lambda, then this is the one way that you can do it. This is not how it's actually done in practice if you have a huge matrix, but if you're trying to algebraically compute it, this is like the main steps. So you get this, right? If you subtract both sides by AU, then this side becomes 0, then you get lambda U minus AU. But whenever you do that, you have to put in the reason why you have to put in the identity to make the math work out. So the identity just makes sure that you're, you know, in some sense, it's just making sure that the two matrices here, lambda I and A, have the same dimension, because you need that for subtraction to work. And if you notice, we have lambda I minus A. That is some matrix, and then it's this matrix times U equals 0. So we talked about a few slides ago this thing, right? AX equals 0, and we need the determinant of A to be 0. So the same thing happens here, except the matrix A that we're interpreting is really just, it's not just A anymore. It's lambda I minus A. That becomes our current matrix. Yeah. And then once you have that, then you can just use the formula, try to solve for lambda. And hopefully it will work out and you don't get stuck with some like heavy algebra. Any question? Oh, yeah, question.
You have 90 vector 1, negative 1, is that equivalent to, say, negative 1?
So are you talking about ordering the eigenvalues or?
Like when you solve for an eigenvector, like you have your eigenvalue.
Yeah.
You go through that.
Yeah, right, okay, so you get multiple eigenvalues, right?
Yeah.
So there you don't get it. It doesn't really matter if you're just trying to get what are the set of eigenvalues, you don't need to worry about the ordering. Sometimes you have to be. Sometimes you might want to be careful about the ordering to make sure that when you're decomposing a matrix into like a singular value decomposition, for example, the matrix that's in the middle might be ordered so that the largest eigenvalue is first and so on. I don't have some stuff on singular value decomposition, but if you're familiar with that, hopefully it's somewhat clear. It's a way of decomposing matrices and yeah, another way that eigenvalues are useful is that they're often they're often the value that maximize a quadratic form, which we will cover soon. Yeah. Yeah. So actually, let's do a quick calculation. So just to make sure that you've gotten it down cold. So what are the eigenvalues of this matrix? I'll give you, how long do you want to do this? Maybe about 30 seconds. So yeah. I'll pause until I see most of the pin like not moving anymore. So. Yeah. So I actually have it on multiple lines. So maybe if you've only gotten to this step, then hopefully you got to here. So you have the determinant of lambda I minus a, and then just plug in the value. And then you just do the algebra to get determinant of this matrix. And then you do like, hopefully you do this kind of intuition about, how to compute the 2x2 matrix determinant from that. And then you get the lambda 1 and lambda 2. So it doesn't matter which one you assign to lambda 1 or lambda 2, as long as you've got -1 and -2. Yeah, so hopefully you got most of this, if not all of it. Yeah, I think the homework assignment has another example where, it might be a little bit more complicated than this. But the homework will give you another example exercise. Yeah, so some other properties of the eigenvalues and eigenvectors. So if you have a square matrix A, then the trace is the sum of the eigenvalues. So, normally, remember that the trace is normally the sum of the diagonal elements, but you can actually just equivalently write it as the sum of the eigenvalues. And the determinant is the product of the eigenvalues. So again, we had that nasty formula that you saw for like 3x3 matrices, and then become worse for 4x4. If you want a simpler way to compute it, just sum up the eigenvalues. Yeah, and you can write out all the equations simultaneously. So that's what implied by the AX equals X lambda. This is capital lambda, I think. Or yeah. No, by the way, this is also whenever you see that symbol of a matrix, usually it means eigenvalue. So normally A is like some number, X is something we're trying to solve, and then this is like some eigenvalue or a set of eigenvalues. So does everyone see why this implies collecting all the eigenvalues and eigenvectors together? Like if you have, like this. So this is for one eigenvalue and eigenvector. And then if you consider the full matrix X as having all those X's, then you get like AX is basically, all of these terms, right? So that's what you get with AX. So, all right, so quadratic form. So some matrices, if they are symmetric, they might be positive definite if for all non-zero X, it is the case that X transpose AX is greater than 0. So a symmetric matrix, A is positive semi-definite if it's the same thing, but you allow it sometimes to be equal to 0. And then, yeah, what does negative definite mean then? So if you see, if you have the definition of positive definite, what does negative definite mean? Yeah, it's the same thing except it's less than 0. And the same thing if it's negative semi-definite. So, and if you're wondering about how to like write this out more explicitly, like with all the sum, like this thing here is the same as this. You sum all the rows and columns and you get aij times xi and xj. So, but usually writing it by x transpose ax is simpler. All right. What about this matrix? Is it positive definite? I'll give you a second to think about it. This is not graded, don't worry. Anyone? All right. Does anyone want to say something about what they think about this matrix? Or you can also write it down if you don't want to raise your hand in the Google Doc. All right, so I see that it's going to be either I relent and go first, or someone in the class says something. All right. I'll give you like 5 more seconds. All right, this is the result. So let's think about this. X transpose AX. X transpose. No, you have X in X1 and X2. Right? So this is taking the transpose of that. And then you have A and then X. So when you do this multiplication, so this thing becomes X1, X2. It becomes like this. And then you do this arithmetic, you get, you basically, by standard matrix multiplication, you get, X plus nothing, so X1, and then 2X2. And then you have X1 times X1 plus 2X2 times X2. So you get a positive number plus a positive number. Unless X is 0, but the definition is only for X non-zero here. So yeah. So hopefully that's all clear. Right. So I think a lot of the subjects that we talked about, they're covered in some introductory like linear algebra courses, but at least for robotics, sometimes we see a lot of derivatives on matrices or gradients on functions. So those are especially important for us to know for this class. So the derivative of a matrix is one where the elements are differentiable functions. Is this matrix here. So AT is the matrix. A dot T is the matrix derivative. And for all combination of the rows and columns, you just take the derivative with respect to T for the individual item. What's the matrix derivative of this? Everyone got it? So you basically go to for each component individually, you take the derivative with respect to T, and then you get it 1 to T 7 0. So all right, gradient. So not to be confused with the matrix derivative. So this is a derivative on a matrix where it's just a matrix. This thing it's like a derivative, but it's on a function that gives you a real value. Right? So, but this is really important to know correctly. So the f here is a function that takes in some vector x and it outputs a real value, a scalar. So the gradient does not make sense if the output is a vector. So if the output has more than one item. So it's only if you're taking a vector and you produce a single number after that. So the gradient with respect to x is this vector of partial derivative. So the way to think about it is you have, and by the way, this is how we write the notation. So if you're using LaTeX, if the nabla, so that's how you would write it out and type it out. So it's this vector of all the partial derivatives where you have f of x and then you differentiate it with respect to x1. So remember, x is this big vector. X1 is a scalar. So dfx over dx1. Same thing for all the other rows. So in principle, it's a natural extension of partial derivative to functions of multiple variables. Yeah. The main tricky thing is because of notation and trying to collect larger numbers. So no, any question on this definition? All right, here's another example. What's the gradient of this with respect to x? Yeah, so I'll give you a couple seconds to work it out. All right. Everyone got it? Most people are not reacting. So I think it's good that our class is at 5 o'clock because I think that's when most of you have like maximal awareness instead of like 9 a.m. So hopefully it's not because of being tired or whatever. I think a couple of people may be working on it. All right, so that's the result, right? So you take in the gradient of x, and then it's df over dx1. And when you're doing that, just make sure that it's always in the column vector. So sometimes people write it as row vectors, then they put the transpose, but I find that to be a little bit confusing. Just write it as I recommend just keeping everything as the column vector. And then that's basically going to be the correct way to think about it. What about these? Everyone got the first one? I'll do it on the board if it helps. Uh, Did everyone get this? Right. So this is how to like algebraically write it out. So you just B transpose X is just this, it's a dot product. And then you have the same thing, and then you differentiate it with respect to different things. And because X1 only appears in one term, then that's the only thing that contributes to the derivative. So you get B. And if you do it with X transpose AX, you should get the same thing over there. It just maybe it requires a little more, notation and writing things out. Yeah. Any questions on this? Hi. So the next step from a gradient is the Jacobian. So remember that the gradient is only defined on real valued function. So the function has to take in some vector and produce some scalar. But the Jacobian will apply even if the function is vector valued. So that means it takes in a vector and produces another vector. And the Jacobian is that m by n matrix, which looks like this. So you have the way that I wrote it is that there's a bunch of rows, but each row is like the gradient transpose. So you get a matrix, and I wrote it out more fully over here. Yeah. So just think of, this is a function of x with g as the vector function, where g is a function, but you can subscript it as g1, g2, and so on to get all the individual items. And that's why it makes sense, that's why g1 is going to be the single scalar, because then it'll make sense to apply a single derivative on it. Yeah. So what's the Jacobian of that vector function? I'll give you a couple seconds to work it out. So what if I said that after you do this, you have to tell me what the solution is, and it's going to be graded? Right. Everyone made some progress on that. I can see most people are finishing up, I think. So. So for the first step, you have G1x. And if you take the gradient of that, then you get, you get it x1 and times x2 plus x1 squared. That's the G1. And then the gradient is basically this term because you're only considering this part. And the same thing for G2, we only consider the x1 to the fourth power. So it's 4x1 cubed with 0 as the second item. And from there, we can just use, this formula to get this Jacobian matrix. So the Jacobian matrix plays a big role in, any areas of robotics, just like the normal gradient does as well. All right. Yeah, question? All right. So you mean this one, right?
Yeah.
One, two. This thing is x2 plus 2x1. This goes away. Yeah, it should be x1, right? Because the partial derivative x2 of this term. Yeah, and then you just keep this. Yeah. Yeah. I'm trying to make sure that the recording will capture this. So I'll do some stuff on the Blackboard sometimes, but it might not always be in the recording. So just be aware of that. All right, any other questions? All right, so I think that's all we have for the linear algebra review. So we cover some basic matrix and vector properties. We cover some matrix algebra and matrix calculus. So that is especially important for a robotics course as well as a machine learning course if you also taken like machine learning here. And so yeah, this is one of the key areas of math in general. So I'm hoping that this course is also one that helps to strengthen linear algebra skills as well as probability skills, which we will cover in the next lecture on Wednesday, because we don't have class next Monday. So it'll be on Wednesday when we meet again. So with that, that's all I have for today, and thanks for showing up. So I'll see you Wednesday then.